Okay, some of what we're talking about today in today's lesson we've already talked about. So we'll just formalize it. But there were 3 ways, just to review here, going back to the last text, 3 ways that we talked about that continuity could fail. Do you remember what they were? Okay, that's getting into differentiability, so I like the way you're thinking. But just for continuity, there are 3 of them. Jump, pull, group class. So those are the 3. There's actually another one called oscillate. I was going to talk about that, but those 3 were the 3. So I think there's a question on there where I had 2 of 3 of those on there. So it was the removable or pull, and then the vertical, and then we didn't have anything about jump. But those are the 3 places where continuity can fail, and there are actually 4 places where differentiability can fail, and we've talked about 2 of them so far. We talked about 2 of them. So I've got some options here. Let's see, what are the 2 we've talked about? There's vertical tangent is 1. And, okay, we got to get all these functions up here. Okay, let's get all the functions up there. Can't really hear the balloon popping. You missed the balloon popping. Yeah, that's crazy. Oh, on my computer. It's your speakers. Oh, it's here. The important things in life.
You're right.
It's not very loud. Yeah, let's do this. We should be able to switch speakers, headphones. There we go. Let's see now. A little better, but yeah. Yeah. I don't know why I have the balloons on here. Alright, can you guys see the function? This was the younger, cooler me that created this particular set of notes. If I created it here in my second go around of calculus, I would have just left the balloons alone. But there you go, for your sake here. Or maybe just for Gemma's sake. So there it is. 4 functions. 4 functions. Using your knowledge of these functions, I think you might know what most of them look like. There's a couple in here that might be questionable. What we want to do is we have these 4 functions, and we're going to drag the text over here, and it'll give us a green arrow to spin it correctly. But 2 of these we've already seen, so we can eliminate 2 of them maybe. You see the corner showing up there. Do you see the corner one?
Yeah, that's the first one.
First one? You want somebody want to come and drag corner to that first box?
Corner.
Oh no, it's the other way around. So here's how it works. I know I have no. So we're going to take corner and drag it to the box underneath the function that it goes with. Take corner. Excellent. So we've seen this one. So this function looks like this, right? And we have a corner right there. And so differentiability fails at a corner y. Okay, maybe you want to say that? Different what? What's the it? The derivative, which we learned is the slope of the tangent of the curve. So clearly the slopes are different to the left and to the right of the corner, okay? So that's one place. But notice it is continuous. Okay, so does continuity imply differentiability? Not necessarily. Here's a counterexample. All right, what about the next one here? F of x equals x to the 2/3. You might have to graph that on your graphing calculator. Once you do that, Why don't you do that? And then I need somebody to come up here and draw a little sketch of it, and then make a guess as to which one of these might fit of the ones that are left. So go ahead and graph it. We'll get a picture of it up here. We've just got these three types of failures of differentiability down here, and they're each going to match up with a function. These are just sample functions for each one. There's actually others that work, an infinite number of other functions. But these are basic graphs that fit the bill. Yeah. Can somebody come draw our f of x equals x to 2/3 up here in green? I can draw it up here in green. I'll get the green up here. You don't have to. I got the pin set up. It was my fault the last time. Oh yeah, there it is. It's a bird. It's a bird. Okay, somebody besides Eric, come on up. See if you think which one of those words might match that one for the failure. Now, clearly, the slope from the left of this point, where the body of the bird is negative. You see that? Like the slope of the tangent lines of the curve are negative, and to the right they're positive. So, you know, the derivative on the left and the derivative on the right of this special point doesn't match. Do you have a guess as to which one of these it might be? Gus? Okay. Super. Go for it. Good job. Okay, next one. F of x equals x to 1/3. You know what that looks like? It's cube root of x function. Does someone want to come draw that? Sketch that in green up here. Sketch it in green. Someone can sketch for us. Dave, you want to come sketch it for us? Graph it on the graphic calculator.
Get up there. Don't worry about it.
Just keep your weight. Green. Green, yeah. It's already. You can do it with your finger if you want. It's already ready for green.
Oh, that thing.
Okay, good. That'll work.
You know,
It has some extra curves. That's okay. So it does. Right here is the special. Or so here was the special point. This is the special point right about here. It actually goes or approaches vertical. So this would be an example of vertical tangent. You might want to look at your graphing calculator to sketch that. That's pretty good. You get the idea there. At x equals 0, it gets really close to vertical. It approaches vertically. And then this one right here, do you remember what this one looks like? We call it salt and pepper function. When x is positive, it's at what? I can draw this one. If you go to, you can graph this on your graphing calculator. Yes, when x is positive, it's at 1. Here, so it goes like this. It's undefined at 0, but it goes like that. And then when x is negative, it's at negative. Reason for that is just think about it. If x were, say, 5, you'd have absolute value of 5 over 5, which reduces to 1. If f were negative 5, you'd have absolute value of negative 5 is 5 over negative 5 is negative 1. So that's the salt and pepper function. And this one, by process of elimination, must be an example of a, they just call it a discontinuity. It's a discontinuity or jump. Because every one of these other functions, guys, is continuous. Okay? They are continuous, but they have a failure in terms of differentiability at least a point. Okay, at one point in each case. And then here, it's not even continuous. It doesn't have a chance of being differentiable there at x equals 0.
What is the problem with the point on the cusp case?
Same as with the corner.
Okay, it's just the corner of the curve.
Yeah. So maybe you could reduce it down to 3, and it would be parallel to continuity. But there's 4 places where, so guys, you're going to be asked to just graph some functions with your graphing calculators. It'll be some new functions, some you're familiar with, and then decide if they are differentiable everywhere or not. And if they are not, why not? So forth. So that's in there. All right. The question here is just the question: does continuity imply differentiability? What's the answer to that? If it's continuous, does it have to be differentiable? If it's continuous at a point, does it have to be differentiable at that point? No, it could be a corner, a crest, or a vertical tangent. So it doesn't have to be. Here's a special function I'd like you to draw. It's just a special, I guess, piecewise function. It is a function. It passes a vertical line. I got an open circle here and a closed one here. So it passes the vertical line. Human way? Probably not. So we're going to list all points for this function for which it is not differentiable. Now, then we should probably say why. So here we have a discontinuous function. It's discontinuous at one point. Everywhere else it's continuous. Where are the points at which this would not be differentiable? And then why? It's not differentiable at, okay, x equals 0, y? At x equals 0, okay, at x equals 0, it's actually not a corner, it's a cusp. Okay. Yeah, but cusp / corner, but yeah, it's a cusp. Just because it's a curve coming into a line. If it was a line and a line, it would be a corner. To be technical about it. And then right here at x equals -1 is the other example, and we would say it's, that's it. I want to show you one more thing, just to back up here. Can we, even though we haven't gotten the power rule yet, let me show you something. Give everybody get a chance to just sketch out. Let's give everybody a minute to finish sketching that down. But those are the types of questions they're going to ask in the textbook. Yeah. There's one more, and then the last slide on. I have one more example. Oh, is there one more place where it's not differentiable? What were you thinking? So -2. I guess if you argued that if you could argue that it was a cusp, it's not. I don't think it's supposed to be. I think it's supposed to be a nice curve. Yeah. So I'm sorry if it looks like a cusp, but yes, you would be right if it were truly a cusp. I think they'll make it very clear. But yeah, it's a horizontal tangent there, and that's fine. There's a question like that on your little formative assessment. Okay, going back to this guy right here, just for Dutch. Looking at these two functions, okay, let's think about what you did in the little practice you had at the beginning, right? With that, remember the x to the 1/4, or the 4th root of x, you were able to differentiate it by bringing the 1/4 down, x to the -3/4. You could do that with this. So if you take the derivative of this is an explicit function, not a picture like on the next page. The derivative would be 2/3 x to the -1/3, which would do what with the x? Move it down to the bottom. What did you just find when you got 2/3 x to the -1/3? The derivative. But when you got it, the explicit function for it, you would have to move the x down to the bottom, which it would be undefined at what value? X equals 0. So there's another way to think about it. Same thing here, right? What's this going to be as a derivative? -2/3, right? Which would move the x down to the bottom. Once again, we've got an issue at x equals 0. So when it's an explicit function that you can find the derivative of, if it moves, if you get a negative power on there with the power rule, moves it down to the bottom, you've got a problem there. It's not differentiable. It's not defined. So just last thing here, does differentiability imply continuity? What do you guys think? Does differentiability, so in other words, if it's differentiable at a point, we got to go point by point here, or at all points on a domain. If it's differentiable at a point, does it have to be continuous at that point? Yeah. Think so? If it's the question is, does differentiability, in other words, the fact that it has a derivative at a point, imply continuity at that point? So what makes it differentiable? First of all, from our homework. Remember from our homework? That is that number 26. I'm so glad you guys asked that. 26 or no, it was 30. Actually, it was 31. That was the one I did. That was already on there. So it had to be, first of all, we had to be able to plug in the point and they would match, right? And then also the slope on the left equals the slope on the right. So if it's differentiable, in other words, to be differentiable, you'd have to be able to plug in the point in question, and both parts of the function would actually have the same y value. So that just brought them together, right? And then differentiability is even stronger than that, because then the slope on the left and the slope on the right has to be the same. But what happened is it had to be continuous. Right? So differentiability does imply continuity, even though continuity does not imply differentiability, that we saw in those first 3 examples, right here, right? Continuity does not mean it's differentiable. These are each continuous everywhere, but they're not differentiable at some point. But differentiability does imply continuity. As a matter of fact, it's a theorem. It's a theorem that, so if you do not have a cusp, corner, vertical tangent, or point of discontinuity things, then the following theorem is true. Make it bigger here. So if f representing a function, has a derivative at x equals a, remember, once again, this is just like the continuity definition. We're looking at it just point by point. But at x equals a, then f is continuous at x equals a. So that's kind of, if the derivative exists at that point, then the function is continuous at that point.
Good job.
Or you're just trying to get as much of the population as you push. Okay, and then one more thing in this unit, you're going to be asked to go back and do what we did on Monday, and that is, in your calculator, plug in the function and find the derivative one of those 2 ways. Okay, so for that TI-83, I have, these are old school notes, so I have like the inputs that you need to the TI-83. They look like most of you had TI-84. So do you know how to calculate the derivative with the calculator at a point? Okay, and you can do it with the second calculate dy dx, and you can do it under the math menu and deriv, right? Because I'm going to ask you to do that in the homework. And we're done. That's it. So in the last 15 minutes, 20 minutes or so, you can either work on the assignment, get some help here in your study groups, or finish up the computer stuff that needs to be done here. I haven't closed it off yet. I'll probably just leave it open for the whole unit, but so just either one.